Hello, I'm Doug Montgomery. I'd like to welcome you back to the Fireside Chat for January. This is the first one of 2026. Uh, I always host this session with a guest speaker, and we explore topics and real world applications of experimental design concepts. We always have some time for Q&A. So whether you're taking the Coursera courses or whether you're applying experimental design methods in your work, or simply curious to learn more about, what is this all about? This is a great opportunity for you to ask questions and engage in some discussion with us. For those of you that can't join us live, we always post the Fireside Chat recordings on our LinkedIn page, which is linked to our YouTube channel, and we share the link in the meeting chat. For participants from Coursera, these recordings are available in your course under the Resources tab. Quick reminder, please keep your mics muted and your cameras off during the session to avoid any disturbances. I've had some Zoom meetings at home where my dog decides to start barking, and it's a big distraction. Okay, so let's try to avoid those kind of things. If you'd like to submit a question to either me or our guest today, please do that using the chat function on the Zoom menu bar. And you don't need to wait until the Q&A starts to do that. You can start putting a question or questions in any time during the Fireside Chat session. And we'll try to answer the questions that come in during this time, but if we can't get that done, we will respond to the questions in Coursera for those people that are enrolled. I'd like to introduce my guest today. My guest today is Ron Snee, and I'm really pleased to have him as a guest. He's an honorary member and fellow of the American Society for Quality. He's a fellow of the ASA, that's the American Statistical Association, and the American Association for the Advancement of Science. He's also an academician in the International Academy for Quality. He's the recipient of the ASQ Schuart Medal, the Grant Medal, and Distinguished Service Medal, the ASA's Deming Lecture, Dixon Consulting Excellence, and the Jerry Hahn Quality and Productivity Achievement Awards. He's won all the major awards in the field. He's authored or co-authored 10 books and more than 350 papers in the field of statistics, process improvement, quality, and management. And by the way, Ron, Cheryl, my partner, asked me to tell you that she is using your Six Sigma book with Roger Horrell for like the umpteenth time in our
Great.
graduate Six Sigma.
Love it.
And she said it's absolutely the best work on the subject in terms of integrating and explaining the management aspects of Six Sigma. It's really well done. And she's been engaged in doing that for Motorola for many years, and the Bank of America for many years, and then teaching here for about 10 years. So she's got a good grip on what works, and your book is a favorite. It's a real terrific book, and you should get a lot of recognition for that. Uh, as I said, his work has been recognized by many professional awards. Ron got his BA from Washington and Jefferson College, and MS and PhD degrees in applied mathematical statistics from Rutgers. He's also served as an adjunct professor in the pharmaceutical programs at Temple and Rutgers University. And I first ran across Ron when reading some of his papers about mixture experiments. And he's just made contributions on a lot of different fronts. And I'm truly pleased that I was able to convince him to join us for a fireside chat today. So with that, Ron, I'm going to turn it over to you.
Okay, let's see if we can get this going. Thank you, Doug, for that very kind introduction. And thanks to your partner for using our Six Sigma book. That's also co-authored with Roger Hurl and Doug mentioned Roger. We've been working together for a long, long time, and it's always always a pleasure. The topic today is screening experiments. And while I was thinking about it, when did I run my first screening experiment? Well, believe it or not, that's when I joined DuPont in 1968. So it was a while ago. And so I've been using screening experiments and pleased to share my experiences with you today. Screening experiments is just very simply, you got a lot of potential factors, and what you want to do is you want to screen them because they're not all important, even though you think they are. Typically, the number is somewhere from less than six, typically in the range of 3 to 6. Factors will have big effects. This is another way of looking at it here. Here we have thinking schematically of 9 factors, and we got three big ones, and of course, one factor is bigger than the other two. Um, so objectives, what we're going to talk about here today is about recognizing the sequential nature of experimentation. Problems are not solved with one experiment. They're rarely solved. Usually takes more than one. We're going to talk about understand the role of screening as an integral part of strategy of experimentation. This is a key word. If you got a notepad, write down the word strategy and draw a circle around it. That's really important. And the whole idea of getting the right data in the right amount at the right time. That's how we effectively solve problems. We'll also talk about develop an appreciation for the Pareto principle as it applies to screening experiments. We'll talk about the robustness of screening designs to assumptions. And we'll see the benefits of screening experiments in several case studies that we'll talk about. We need to think about today's realities, and the bottom line is, as I mentioned just a moment ago, we need to get the right data in the right amount at the right time. And how do we do that? Why do we need to do that? Well, we've got strong competition around the globe. We need to move quickly to remain competitive. Products and processes are getting more and more complicated. And so we need a strategy that enables us to get rapid understanding of process and products while reducing the time to market. Anytime you start talking about process and products and experimentation, I go back to the iterative nature of experimentation, which George Box introduced in 1957. The schematic you see here was created by Horace Andrews, who was my major professor at Rutgers University. And so you look at that, and you see we're iterating between the experimenter's world of observation, and we're doing that by creating hypotheses, designing experiments, conducting the experiments, do the analysis that generates future hypotheses and more designs and more experiments and so forth. And you see, so you start off with ideas and conclusions and inferences. All along, you go up this this hill here, so to speak, and you're building knowledge about the products and processes. So your gut knowledge is building as you go up this hill. Science is helping you test and create hypotheses. And a critical element here is the design and analysis of experiments. This is really, I think, this is a nice way of thinking about the whole idea of Box's idea of iterative nature of experimentation. The other important thing is that people are driving this process. It's not going on by itself. So that's the reason you see we've got these characterization here. So it's people driving these processes. So some critical issues that we need to discuss. One is a unifying strategy of experimentation that integrates experiments with other types of experiments. We'll talk about running experiments, the theory and the benefits, talk of the Pareto principle, graphical display of results. We'll talk about that. We'll talk about the whole idea of screening experiments when you have to deal with or think about curvature and interactions. And then, of course, the next steps after screening, are you going to run additional experiments? You're going to run confirmation tests, what have you. So those are some of the critical issues we'll talk about. I want to begin with the strategy of experimentation. I ask you to write that down and draw a circle around it. Strategy, what is strategy about? The best way to think about strategy is the plan for how we're going to win, how we're going to be successful. If you go back a long way to World War II, the Allies, what did they do? They had problems with, they were fighting the war in Europe, and they were also fighting it in the Pacific. And so their strategy was, we will win in Europe first and then move to the Pacific. So what does that tell you? That says that whenever you have a problem, you need resources or whatever, Europe gets the first cut of the resources, and whatever left goes over to the Pacific. Now, the folks in the Pacific are not real happy about that, but that was a strategy that the Allies used. So you need to think about a strategy for experimentation. Let's talk about an example here. Start off with one. This comes out of my experience in working with pharmaceutical companies. This company was working with a blockbuster drug, and the product was in late development. As a matter of fact, it had been late development for 8 years, and they couldn't get the validation completed. So they used a screening design to launch this, and they were able to launch the product in really 1 year. The screening experiment, they were at 9 factors, 27 runs, and lo and behold, the results, what did they find? Well, they found one factor that had the largest effect, and this effect was totally unknown before they even did the experiment. So by running the screening experiments, they increased process understanding and what factors were having the biggest effect, identified a previously known factor that's mentioned that it had the largest effect, and information enabled the rapid product validation and introduction. Now, not to say that nothing was learned in the 8 years that they were working on it. They did learn some things, but they just couldn't get it across the goal line. And this screening experiment helped them do this. This just shows you some of out of the 9 factors that they were looking at, there was there 5, 6, 7 had effects in this particular case. And there you can see the big one, process variable number 2, totally not known. The effect of that was totally not known, and the screening experiment identified that effect. So our situation now, when we're thinking about our strategy, is we're experimenting with a large number of variables. We want to reduce the risk of missing one or more key variables. We want to reduce the amount of experimentation. And as I mentioned earlier, I keep coming back to this, we want to get the right data in the right amount at the right time. So this strategy, how we're going to win, we need to diagnose the experimental environment. We need to decide on the quality of the information we need. We need to select the appropriate experimental design. You need to conduct it and then run confirmation tests or additional experiments. There's a lot of people that for some reason they don't get around to running confirmation experiments, and that's a big hole in their strategy in my experience. So here is looking at the experimentation as it depends on the environment. So if you looked on the left-hand side over here, experimental environment, you got number of factors, desired information, model form, experiment design, number of runs. And then the environment, we divided up into 3 phases: screening, characterization, and optimization, which are a function of the number of variables. If you have more than 6, we say you're in a screening situation. Characterization, 3 to 6, 2 to 5 for optimization. Now remember, this is a strategy, and this is not perfect, but this is a strategy that's been very effective. Matter of fact, I'll say I was introduced to this strategy when I came to DuPont in 1968. And they had already developed it almost, I would say it was 90% developed whenever I got there, and I was able to participate in getting it completed. But that's not important. The way to think about this is if you go back into whenever you have more than 6 variables, you begin by screening first. You're looking for critical factors, factors which have big effects. The model that you're using is a linear or main effects model. The experiment design is the Plackett-Berman, the candidate experimental designs, the Plackett-Berman, fractional factorials, the definitive screening. And typically in the screening phase, you're going to run 8 to 32 runs. When you get over here to characterization, you begin to look at linear and interaction effects. You're going to be running roughly 12 to 32 runs. And then when you get over here to optimization, you're going to be doing response surface designs and 12 to 40 runs there. So now I started to say, just finish it. This whole strategy developed at DuPont in the early 60s, mid 60s, and it's been used ever since. And it's the way I think about experimentation and strategy of experimentation, how you're going to win. An important part of all of this is process understanding. And process understanding, as you can see on it somewhere here, process understanding is a function of the number of variables. And so you have to think in terms of that. And so if you're in the situation where you have more than 6, which we talked about just a moment, you have fuzzy process knowledge. This is in a screening situation. And there's a great quote by Russell Ackoff. He says, the less you understand about a phenomena, the more variables we require to explain it. So typically, you don't have a lot of understanding, you're going to have a lot of variables you think are important. If you increase the understanding, and so you have useful process knowledge, 3 to 6 X's, that's in the characterization phase. And then finally, when you get it down in the 2 to 5 range, you're in the optimization. So this is a good way of thinking about how process variation, process understanding, and number of variables relate to one another. Now, this strategy it really has 7 different options. Option 1 is kind of the one which I showed you a moment ago. You start with screening, you move to characterization, and then optimization. The second strategy is you start with screening, and then you move from screening over here to optimize. Third one here is screening to characterization. Another one is you start with characterization, and then you move to optimize. And then the last 3 is you might start in screening and solve the problem, take action at screening, or maybe it's with characterization, or maybe you're in the optimization phase. So it depends on the situation, these different options. For instance, here, the number 2 one, where you do the screening experiment and then you move to the optimization. Some people seem to think that's the only option there is. I've used that quite a bit. That first example, that whenever I was using screening and that DuPont example, that's what I did. We went from screening to optimization. We screened 13 variables. I think it was 24 runs. And then we moved to optimization. We picked the 4 big ones, 4 important ones in screening, and that's what we did the optimization with, using a Box-Benken design, which many of you are aware of. The other point I will make is that down here, number 5, just working with screening, I've seen a number of problems, and I'll show you some examples where screening solved the problem. So it has an advantage there. And of course, the bottom line here is the strategy selected depends on the project objectives, what strategy, what phase you're in, and the results from previous experiments. So you got to worry about that and use that information. Now, rather than waiting to the end, let's talk about now what are some of the resistance that you see to using screening experiments. The first one is that a lot of people, and the way they behave and the way they work, it's clear that a number of variables is too complicated. They just don't want to deal with a whole number of variables. Like I just mentioned that 13 variables, that would really be complicated. I think this other here is I think it's a lack of adventure mindset, too much conservative, being too conservative. And so using screening enables you to be more adventurous. There's a concern that important interactions will be missed, and I think that's a little bit overblown. We'll talk some more about that a little later. Also, they're worried about not only the interaction, but there'll be curved response surfaces, and that'll be a problem, typically when you're using two-level screening experiments. And also worried, most screening experiments, a lot of we'll talk about, are two levels, and they're worried that there's a problem if you you have a design which is a power of two, and of course that's not really a problem. And a popular design, which I mentioned earlier, and I'll show you an example here in a moment, is the criticizing the Plackett-Berman designs, and we'll talk about that as we go along. So here's one. This is a marketing advertising study, and they screened 19 factors in 20 runs. And this is the response was the advertising response rate. And so what they were trying to do was find different ways, if I can find my notes here, is that they had they were sending out, I want to get this right. Anyway, so they're sending out advertising for credit cards, and how are they going, this larger number of factors of why people are interested in credit cards. And so this studied 19 factors in 20 runs. That's a Plackett-Berman design was used. Here it is. You see the code of the variables A through S and the factors, and the control level was, this is how you can think of it as this was how they were generally doing it. And this was the new idea that they wanted to test out. And so when they did that, and they created a Pareto chart of the effects, you get Pareto charts of effects, you get that out of standard software. And you see there's 5 large ones here. And so those 5 large ones were factors T, G, S, J, and K. And we'll talk about those a little bit more in a moment. But the key thing here is these are large effects. You hear people talking about these are the big bars on the Pareto distribution. The only problem is you don't know whether those bars, whether the effect is positive or whether it's negative. So this is a plot that I use on basically what you see here is you've got the effect and you've got the confidence limits, and you rank the effects just like you saw on the Pareto chart. So you see the 3 largest ones are negative effects. So you wouldn't want to adopt those. Then you have a positive effect. Then you have a negative effect. And then the rest of them are buried in the noise. Now, as I said earlier, there's theory, experience, and so forth that you're typically going to see somewhere around 3 to 6 important variables. So in this particular case, we have 5. These 5 effects, are the interest rate, the sticker, buck slip, copy message, and so if you just go back a minute here. So that's what these effects are, the names for these effects. So then if we go a little bit further and we look at these, and so here are the factors, the interest rate, the big one, these are the top 5. And then if it's low, or if it's red, We don't make any change. We just stick where we are with the control. And if it's black, then that says we're going to use the new idea. And so in this particular case, the top out of the top five, four of them had negative effects. We saw that right there. See, four of them, these three and this one, and then there's got this one, which is the copy meshes, target and generic. And so they would adopt the new idea of generic. And the other 14 factors, you'd consider which levels you want to use in the future. Since they had no effects, you can stick with the control. You can use the new idea, whatever. But the statistics is not telling you which one to use, other than strongly consider here the copy message. Now, another aspect of using screening designs is, are they saturated? What do we mean saturated? It means that you have as many factors as runs. Actually, it's one less than the number of runs. Now, in the marketing advertising study that I just showed you, there were 19 factors in 20 runs. And they're really helpful when it's believed there's only a few factors that are going to have any effect. So here's another example. This comes out of a chemical process, actually the old Union Carbide down in Charleston, West Virginia, which was published by Hendricks, and got a new process. It's not meeting the quality goal of 22 units. So they wanted to have 22 units measure quality. 15 factors were identified. They used a 16-run screening experiment. And the results of the experiment showed 7 of the 16 runs had quality values greater than 22. So remember, the goal was 22. So you had 7 that had runs that had greater than 22 units. So right away, you could look at that and you say, hey, we got a chance of being successful here. Well, it turned out when they did the analysis, 2 of the 16 variables had significant effects. The other should be 2 of the 15. The rest of them didn't have any effect at all. And 2 of the combinations of the 2 factors had all the values were greater than 23 units. Of course, there's analysis with all this, but you can just simply look at the data and you can see these results. So, problem solved, case closed. Screening experiment, got the data, looked at it, and they got useful results. Now I want to show you some information on screening experiments and some important issues that we need to pay attention to. And these are testing the Pareto principle, robustness of screening experiments, one-shot strategy, and test method robustness. So let's look at the test principle, look at the Pareto principle first. And so what I did here, okay, so the Pareto principle says that you're going to have a small number of important variables. And a lot of people had, particularly in the Six Sigma world, had been using the 3 to 6 number, that you're going to have, typically you're going to have 3 to 6 important variables. So I decided to test this out. I went to the literature and I found 47 screening experiments. There were 5 different design types: fractional factorials, Blackett-Bermans, Taguchi, definitive screening, and so forth. And the design size was somewhere between 12 and 64 runs. And the number of factors were 9 to 23. Now I selected that 9. I put a lower limit of 9 because I wanted to have the chance of really finding out really how many variables were important. So this is what we found here. And so here's the number of big effects and the frequency. And so you can see here's 1, 2, 3, 4, 5, 6, and so forth. And you can see the majority of them, of these 9 or more, the majority of them are 6 or less, just like we thought. So our conjecture was 3 to 6. The median value was 5. That's right in there between 3 and 6. 55% identified had 4 to 5 factors. 91% had the 6 or fewer. So if you take 6, the whole 91. So the conclusions say the data support the conjecture of 3 to 6. So what that says is if you think you're faced with a lot of variables, like that one we just showed you had 15 variables in it, 19, not to worry, because there's not going to be 19 important ones, or there's not going to be 15 important ones. There's typically going to be 3 to 6. And here's, and I did this study here and to prove it, which proved what was kind of like common thinking. So that says, hey, that these screening experiments can really be useful. The next thing I want to talk about is the robustness of screening experiments. And everybody's worried, well, I can't run screening experiments because I'm going to miss important interactions. Well, it turns out if you have large effects and you fit an additive model to the large effects, the additive model is going to identify where you have the interactions. Now, it's not going to model. Obviously, the linear model won't completely model the interaction, but it tells you whether you might. It doesn't mess up the results. This is a real interaction that we have here, and if we look at the blue, here's S at the low level and S at the high level, and you can see the interaction. And then the additive fit is going right in the same direction. So whenever you did the analysis using the linear model, you're going to find both the S effect and the G effect. So you're not going to miss many interactions. Now, there's something called the scissors interaction. If you have a scissors interaction, the linear model is going to miss it. But so there's no guarantees in life, and there's no guarantees using screening designs, but it's a good way of working at it. Another one that people are concerned about is curvature. What if we have curvature? Oh my God, what do we have curvature? Well, look at this response. Here is, if you look at the blue dots, we got a curved line here. But if you look at the linear effect is going to pick up the curved line. It's not going to pick up the curvature, obviously, but it picks up the overall effect. So you're not going to miss much curvature, unless, again, there's the case that if you had like like an umbrella effect, it goes up rapidly through a maximum and comes right back down, you'll miss that effect. But hey, like I said, there's no go guarantees. The other thing is I did a study, which I don't have time to go into right now, maybe in the discussion, but linear effects generally dominate interaction and curvature effects. So in those 47 experiments that I looked at, in some others that I've looked at, the linear effect dominates the curvature effects. So maybe we'll have a chance to talk about that in the. So here is in the paper, and there's a reference to this work at the end, and so you'll see that So here's the case studies in the paper, the advertising we talked about. There's one wastewater discoloration, boiler water gas test method variation, glass metal screening, material screening. And so what do you see from that? Well, the number of X's here varies from 7 to 19. The big effects, 4 to 5. The number in the screening was, what's it got down here, 16 to 27. The different designs that were used, Plackett-Berman definitive screening, Taguchi, two-level factorial. And then the uniqueness of these particular examples, saturated design, use of definitive screening, Taguchi, test method robustness, I'll talk some more about that one, and modal response. So you can see that screening experiments can be used in many different situations and using different approaches. So very useful tool. Now, let's go to the one-shot experimentation. And people are, matter of fact, there are researchers that what they want to do is they want to find experimental methodologies that is only one shot experiment. And so when should you want to use a one-shot experiment? Well, you want to consider it maybe when there's strong pressure that you want to complete an experiment quickly. And it's complete an experiment and get an answer quickly. Or you've got this experimental region, it's well defined, you know the candidate variables, you know the ranges, and you know the levels. All of this is known, which is in most cases is not known, but you are that situation, that's all known. Confirmation runs can be made to check the model validity. And or model validity can also be assessed through checking the prediction accuracy as the model is used. So sometimes you do experiments, you got the model, and you use the model to operate the process. Well, you can predict over time how it's doing, and if the predictions are good, you probably are in good shape. Now, here's the big limitation, is that the one-shot strategy ignores the sequential learning aspect of George Box's iterative nature of experimentation. And we need to keep in mind that problems are rarely solved with one experiment. I'm going to show you an example, and I've showed you other examples where they have been solved, but rarely are they solved with one experiment. You need to use the sequential learning aspect of the iterative nature of experimentation. That whole idea of starting with screening, maybe going to optimization, maybe doing characterization before you get to optimization. So learning is a sequential. Now I'll show you one. This is out of my own experience. We had 6 plastic molding machines that were used to make a particular medical device. So it's a plastic device, make it with 6 molding machines. So here was our strategy. Here's how we were going to win and be successful. We're going to experiment with one machine and apply the settings to the other machines. That's kind of risky, but that was a strategy. Then we're going to start with a screening experiment. We're going to use a 2-level fractional factorial design and look at the effects of 8 variables in 16 runs. So what would that be? 2 to the, an 8 minus 4, I guess. Yeah, 2 to the 8 minus 4 design. And what did we get out of that? Well, first of all, 3 of the runs didn't work. Oh my goodness, that was really frightening, because these screening experiments, sort of like you want to every point have all the data so that you can get good results. But not to worry, one of the 3 remaining runs 13 remaining runs worked better than anything they had seen before. And so this setting was applied to all the machines, and they were off and running. So we still did the analysis of the 13 runs, confirmed those settings that I mentioned earlier, and the defect reduction was reduced by 90%, annual savings $375,000, and I'll tell you, that was a long time ago. That was when a dollar was worth something. So that was pretty significant, getting $375. $375,000. Let's get the number right. Now, why did all of this work? Well, the nice thing about the screening designs, as with factorials and fractional factorials, is you have a good sampling of the experimental region. And I think that's the reason that this one worked here. All right. Now, one more example and we'll be done. I'm going to talk about test method robustness. This is something that I think the whole idea of test method, the statistical community, in my view, hasn't really paid too much attention to the whole idea of test method robustness. And the screening experiment's a useful tool for assessing that. Jack Uden told us this back in 1961. He defined test method ruggedness, he called it, or robustness. He says a measurement procedure is said to be rugged if it's immune to modest and inevitable departures from conditions specified in the method. Factor labels can be evaluated using, two-level factorial designs, fractional factorial designs. And two-level designs work well because the goal is to assess small effects, small variations in how the test method is being used. Here's an example. Here we have that we want to know how robust, insensitive to the measurement, and small changes in its execution. Here we're measuring percent water in a chemical compound. We're going to make a large batch of the compound, carefully mixed to assure uniformity, create 8 subsamples, 1 test per run. Here are the variables you see, the base condition and the revised condition. And here's the design. So you see you got 8 runs and you got 7 factors. And you see the percent water, not a whole lot of variability here. There's a low of 18 and a high of 20. And you compute the effects and see only 3 large ones. And if you looked at the percent of the effect, here's aniline is a 4.3, and then you got a 3.2 and a 5.1. And in general, a lot of people think about if you got factor effects 5% or less, why you're in pretty good shape, at least from a practical situation. So here's showing the effects. You see here now on this one, we got the upper lower limits are plus or minus 5. And so at the conclusion of this, Wernermont said that we've done this rugged test to sort out those conditions that are likely to require further study or need close control. So in this particular case, in 8 runs, they've found that there's 3 of the 7 factors that they need to worry about, if at all. And so anyway, that's where they were. What they concluded come from this particular test. There we go. There's aniline and distillation time and reagent. So let me wrap this up, that we will have a few minutes for questions here. So when experimenting with a large number of factors, we want to reduce the risk of missing 1 or more key variables. We want to minimize the amount of experimentation. Here are some critical strategic needs. We need to integrate the screening experiments with other types of experiments that we need to do. We need to understand the theory and the benefits of screening experiments. Graphical display and statistical significance of the effects are important. Need to worry about those. The Pareto principle works. Need to understand that and how to use it. Recognize screening experiments are robust, in my view, to curvature and interaction. Probably, maybe somebody will debate that. We can use it and should use it in testing out test methods. And next steps after screening, you may want to run additional experiments. You may want to run confirmation tests. It depends on the situation. So that's my story, and I'm sticking to it. Love to answer any questions you have. This paper, everything that I've said here is contained in the paper here by Steve Bailey and myself, and there's the reference of where you can find it. So with that, Doug, I'll shut up and entertain any questions that anybody might have.
Well, Ron, thank you very much for this really terrific presentation, and I want to put the slide back up that has the reference to your paper with Steve, because I consider that to be a really super informative paper, and I would suggest that anybody that's running experiments should read that paper, because it's got a lot of really useful insight. We don't have any audience questions today, which is a little unusual, but there's a couple of things that I wanted to take advantage of having you here and picking your brain about. And one of them is the idea of non-regular fractional designs. the Plackett-Berman designs are, of course, non-regular designs because they don't they don't have complete aliasing of effects. The main effects are partially aliased with the two-factor interactions. And people have I guess struggled or argued or debated about the methods for analyzing those designs. And I wonder if you have any particular thoughts about analysis methods for designs like Plackett-Berman designs that are non-regular fractions.
Well, I use just the standard approach. Compute the effects and look at where you pick out the most
Mhm.
important variables and so forth. But the important thing, well, a couple things. One is you can look at how well do you fit the data, and if you're getting good fits from the models, I don't know, adjusted R squares of 90%, 80%, that kind of stuff. That's a clue that you've got a pretty good understanding of the data. But the other one is simply run some confirmation experiments. And does this work? Um, I had an example, one that where we were looking at an analytical method. We had something like 7 or 8 variables, and one that they were really concerned about is they it was measurement system. This was a spindle, and they had 2 spindles, an old spindle and a new spindle, but they all look, they were supposed to be the same. Well, anytime somebody says that you have a variable which is not important, everything is identical, right away you ought to be suspicious. So I were able to get them to test that along with it. Well, wouldn't you know, when the experiment was done, the largest effect was the difference between the 2 spindles. And so they wanted to run a test to just prove that out again, and we did. And it just proved, the confirmation experiment just proved the importance of the 2 spindles. So they weren't identical.
Good. Interesting. So we just have a question that popped in from
Ah,
one
good.
of our online people. And I'm going to read the question and like to have your thoughts on this. Says when you have multiple responses in an experiment, have you found that screening experiments still reduce to three to six important factors?
Yes. Yes, the answer is yes. And in the paper, we have an example that demonstrates this. Now,
Ah,
obviously, if you have more responses, that reduces the chances that you're going to have a smaller number of variables, but it's still a good strategy when you have multiple responses.
yeah, I think what I have found is that you still have a fairly small number of factors, but that may not always be the same. You might have a different mix of 3 or 4 factors for one response than you do for another, but there are typically a lot of commonality. There might be 1 or 2 factors that are different for some of the responses, but yeah, I think I would agree with what you have to say here.
And remember, problems rarely are solved with a single experiment.
Yeah.
So based on those results, we'll suggest to you what other experiments you ought to run.
I'd like to talk a little bit with you about that because for the last few years, probably 5 or 6 years, I've had a research project with the Defense Department. And in fact, there's been 7 universities involved in this project. It's an initiative called the Science of Test Consortium. And you'd recognize the people and some of the schools that are involved. Air Force Institute of Technology and Ray Hill has been involved. There were people at Naval Postgraduate School involved. There are people at Virginia Tech and Florida State, and a number of places that have been involved in this. And what we've been working on is methods to improve the efficiency with which the DoD has to run operational tests. And operational testing is something that's required now. In fact, Congress passed some legislation years ago requiring operational tests because there had been many situations where a new system had gone into the field and it had had very thorough development testing. But when it got into the field, it didn't perform the way it was supposed to under uh, real usage conditions, real field situations. And so this operational testing work is fairly large scale. Uh, it's typically done at a test range. So it might be some fairly large scale test facility. You need typical users, and you need the ability to control lots of factors. In fact, a typical OT will have somewhere between 6 and maybe 9 or 10 factors. And so fractional factorial designs are sort of the order of the day. The problem that we run into is that you'd like to use a design that is large enough to capture main effects and give you some idea about two-factor interactions. But because these tests are so extensive and require such a long amount of time, you can't secure the test range for a huge amount of time. These test ranges are scarce resources. And so we end up trying to figure out how to use 8 and 16 run designs. And typically, what we've been looking at are non-regular designs because they do give you some capability to get information about interactions. And we've had some success with this. And we've been looking at using different analysis methods to try to resolve the partial aliasing or partial confounding of main effects and two-factor interactions or two-factor interactions with each other. And we've been using some generalized regression methods. We of course have tried some of the standard things. We've tried some variations of stepwise regression. We've tried the lasso, for example, and had great success generally with the lasso. We've tried the Danzig selector, which is similar to lasso but uses a different shrinkage criteria, and that hasn't worked quite as well. And we're continuing to look at some of these different methods. And I just wondered if you'd ever tried any of these analysis methods on some of the designs that you've been involved with, things like lasso.
No, I haven't. I haven't used lasso. I tend to shy away from the automatic procedures. Um,
Yeah,
so I get very concerned when people want to use stepwise regression. Um,
yeah,
so and well, I'll just take a minute here. Stepwise regression, it's just like going to the rodeo and the bull riding contest, and the rider gets on the bull, the gate opens up, all hell breaks loose, and all of a sudden, either they stop it at 8 seconds or the rider falls off. But now the question is, what the hell happened between opening the gate and the guys
yeah,
on the ground? Well, we don't know. That's
yeah,
automatic procedures don't tell us. So
yeah.
anyway,
Yeah. No, you're right. You're right. And
uh,
and that's why we try to recommend being very conservative about using these methods. The problem that handicaps us a lot is that in a lot of these operational tests, follow-on experiments, either things like fold over or even confirmation testing, is almost impossible because the range time is so tightly restricted. You may run the experiment, and you may get results that look really interesting, and you'd say, well, gee, I'd like to do some confirmation tests. And you talk to the people that run the range, and they say, "Oh, that's great. We can book your range time next August."
yeah, yeah.
I mean that is a real problem.
It's a
Uh,
real problem, and I've seen it in industrial
yeah,
experimentation, the
sure you have.
same issue.
Yeah,
Yeah.
and you know so that's why we're trying to be as conservative as we can, but still try not to leave any stone unturned, you know, in terms of what might actually be in, because these operational tests have huge significance. They really do, and we have seen uh, situations where some of the test methods that we've suggested have uncovered some real problems. The most celebrated one that actually got some popular press was a big problem with the new F-35 fighter. Uh, I don't know if you're familiar with the F-35, but it's meant to be a tri-service fighter aircraft.
Oh, uh-huh.
uh, Navy, Marines, and Air Force flight, and there's only been one successful tri-service fighter, and that's the F-4 Phantom. And so the F-35 has a big role to fill. But when the F-35 first went to operational testing, uh, we discovered that that the Navy Marine version would not land on the aircraft carrier. the,
Oh, oh,
the, the tail hook was in the wrong position.
oh,
The tail hook was too far forward, and
ah,
it had to be relocated, and there was a lot of redesign work, and this had not been caught in computer modeling. It was only caught when you actually tried to land
yeah,
it.
whenever
You
you
know,
tried it. Yeah. Well, the one thing you didn't mention, I'm sure you do it, but I think we need to keep this in front of us, is that you're running in this program, you're running a lot of tests. Remember, I talked about
yeah,
sequential experimentation, problem solving. So there's some things you learn that can be applied down the road,
yeah,
even though the operational tests are different. So we
yeah,
shouldn't lose sight of the fact that you shouldn't have one experiment, devoid of any other information.
right,
I guess
yeah.
that's me. And
You will continue to get information as you go along.
exactly,
Yeah,
exactly. That's what 1957 George Box told us that.
right.
And so need to keep that in mind, and I know you do.
Yeah. Oh, yeah.
Uh,
That's always important.
Always important. But there are some young experimenters that don't have that experience.
Right.
That's the reason I bring the issue up.
No, and it's a good point. By the way, I want to thank you again for coming to spend time with us today. We're running out of time. We've got to stop. Our next fireside chat is going to be in February, and we'll put more information about that in LinkedIn, and you can find the recordings tab for today's class session in Coursera. Ron, thank you very much for spending some time with us. I know this took a lot of work on your part to pull everything together, and I greatly appreciate you spending time with us.
Well, my pleasure. My pleasure. Good luck to
Okay,
you and your organization.
great. Thank you.
Sure thing.
We're done for the day, folks.